Hello everyone, this is Amit Prambhat, and today we are going to go over chapter 4 of week 3 Gates and Circuits for CS 110 at LaurelRidge or VCCS. Let me go ahead and share the screen. Welcome to chapter 4 Gates and Circuits. In this chapter, we'll move from raw electrical signals to logical building blocks that make computing possible. We'll see how simple on-off values, zeros and ones, are shaped by gates, combined into circuits, and eventually scaled up to entire chips and CPUs. Keep the big picture in mind. Logic lets us turn electricity into reliable decisions. By the end of the chapter, you'll be able to read logic diagrams, reason with truth tables and Boolean expressions, and understand how adders, multiplexers, and memory latches underpin everything your computer does. Our first set of goals: identify the basic gates and describe what each one does. Understand how these gates are built from transistors. Combine gates into circuits and describe a gate or circuit using three interchangeable views: Boolean expressions, truth tables, and logic diagrams. Watch for how these representations map to one another. If you can say it as a Boolean formula, you should be able to draw it as a circuit and verify it in a truth table. That fluency is what turns schematic into a predictable behavior. Continuing the goals, compare half adders to full adders so you can see how carry-in changes the design. Explain how a multiplexer selects one of the many inputs using a few control lines. Describe how an SR latch operates, how SR latch stores a single bit of state, and finally, recognize the historical evolution of integrated circuits, the scaling story that took us from a few gates per chip to billions and beyond. These objectives connect theory to hardware you can buy, and they set up later topics like arithmetic, logic units, registers, and memory systems. Computers and electricity. Let's ground everything in electricity. A gate is a device that performs a basic operation on electrical signals. Its inputs and outputs are either low, 0, or high, 1. Circuits are just gates wired together to perform more complex tasks. What matters is that each gate reinforces a precise logical rule. So when we connect them, the rules compose. Think of a circuit as a tiny decision-making network. Inputs go in, logic happens, outputs come out. As long as voltage thresholds are respected, we get reliable digital behavior. How do we describe the behavior of gates and circuits? How do we describe what it does? We use three complementary tools. Boolean expressions give us compact algebra for two-valued logic. They let us manipulate and simplify designs. Logic diagrams show the physical like structure, boxes and symbols with wires so we can implement or debug. Truth tables list every input combination and the resulting output, providing correctness exhaustively for small designs. Practice translating the same idea among all three to gain intuition and confidence. Gates. Here are the 6 core gates we'll use: NOT, AND, OR, XOR, NAND, and NOR. NOT flips a single input and outputs 1 only when all inputs are 1. or outputs 1 when any input is 1. XOR, or exclusive OR outputs 1 when inputs differ. NAND and NOR are the negations of and OR, respectively. They are especially important because each is functionally complete. You can build any logic from just NANDs or just NORs. In diagrams, gate shapes carry meaning, so learn them well. NOT gate. The NOT gate is the simplest one input, one output. It inverts the signal. If the input is 1, the output is 0. If the input is 0, output is 1. You'll see it drawn as a triangle with a small bubble on the tip. That bubble means logical negation. Not is invaluable for expressing conditions like not A and for creating other gates when combined with wiring strategies, as you'll see with NAND and NOR. AND gate. Okay. The AND gate takes two inputs and outputs 1 only if both are 1. Any 0 on its inputs forces the output to 0. In Boolean algebra, we'll write this as AB, meaning A and B. Visually, an AND gate is a D-shaped symbol and captures the logical idea of both must be true, which is everywhere, from enabling a write only when a register is selected and a control signal is asserted to combining bit patterns. OR gate. The OR gate outputs 1 if at least one input is 1. Only when all inputs are 0 does the output fall into 0. In Boolean notation, we write A plus B or for A or B. The symbol is curved at the input side and pointed at the output, or expresses either condition suffices, useful for combining multiple possible triggers or enabling signal that can come from different sources. XOR gate. XOR or exclusive OR outputs 1 when exactly one input is 1 and the other is 0. If both inputs match, both 0 or both 1, XOR outputs to 0. The symbol looks like an OR gate with an extra curved line on the input side. XOR is crucial for parity checking and bitwise addition because it represents difference between the bits. When you add two single bits without carry, XOR gives you the sum. It's easy to confuse OR and XOR because they differ in only one case. When both inputs are 1, OR outputs 1 there, but XOR outputs 0. That's why XOR is called exclusive. It includes either input but excludes the case where both are true. Keep that distinction handy. It directly explains why the sum bit in a half adder is A XOR B, while the carry bit is A and B. NAND gate. NAND is not of AND. Outputs 0 when all its inputs are 1. Otherwise, it outputs 1. Draw it like an AND gate with a small bubble at the output. NAND's popularity comes from an ease of fabrication and universality. With just NAND gates, you can construct NOT, AND, OR, and everything beyond. Many real chips are largely built from NAND structures. NOR gate. NOR, not of OR, outputs 1 only when all its inputs are 0. Any 1 on the inputs forces the output to 0. The symbol is an OR gate with a bubble at the output. Like NAND, NOR is universal, and it appears frequently in control logic and in classical latch designs where the output is fed back to stabilize a stored value. Gates with more inputs. Gates can have more than two inputs. A three input AND outputs 1 only if A, B, and C are all 1. A three input OR outputs 1 if any of A, B, or C is 1. The same truth table reasoning scales naturally. Enumerate all 2 raised to n input combinations and apply the gates rule. Multi-input gates save space, and wiring in diagrams where many conditions must be considered together. Constructing gates. Under the hood, gates are built from transistors. A transistor is a semiconductor device that acts like a control switch. Depending on the voltage at its control terminals, it either conducts like a wire or resists like an open circuit. With no moving parts, transistors switch extremely fast and reliably, which is why digital logic scales to billions of devices. A typical transistor has 3 terminals: collector or source, base, and emitter. When a signal is grounded, it is pulled to 0 volts. By arranging transistors so that a control input opens or closes a path to ground or to a supply voltage, we realize the on-off behavior each gate requires. The exact naming and physics differ across technologies, but the switching model is universal. Consider a simple transistor configuration as shown. If the base signal is low, the device behaves like an open switch, and the output follows the source. If the base signal is high, the switch closes and the output is pulled low. Functionally, that's an inverter. High in produces low out and vice versa. So we have just described a NOT gate implemented with a single control switch and a pull-up path. From these building blocks, the easiest gates to realize are NOT, NAND, and NOR. By combining pull-up and pull-down networks of transistors, designers create paths that either strongly drive the output high or pull it to ground based on input combinations. These patterns are the foundation of logic families and standard cells used in modern chip design. We classify circuits as combinational or sequential. In combinational circuit, the outputs depend only on the present inputs, no memory. In sequential circuit, outputs depend on inputs and on stored state of prior moments. We'll describe either kind with Boolean expressions, logic diagrams, and truth tables, but only sequential circuits require explicit feedback or storage elements. Here is a small combinational example. We can wire gates So the output equals AB plus AC. Read A and B or A and C. In a diagram, you'll see a feeding two paths, one combining path with B and another with C, and the two results ORed together. The Boolean expressions and the diagram say the same thing. Later, we'll confirm with a truth table. When a circuit has three inputs A, B, and C, the truth table requires 8 rows to cover every possible combination from 000 to 111. Filling those rows forces you to consider all cases, and it's a great way to verify your diagram or algebra. If any row surprises you, trace the signal path through each gate to debug. Consider the expression A multiplied in bracket B plus C. It's a truth table, matches the earlier circuit for AB plus AC. Whenever B plus C is 1, the output depends on A. When B and C are both 0, the whole expression is 0, no matter what A is. Seeing this correspondence in the table reinforces that algebra, diagrams, and tables all tell the same story. Why did those two circuits match? Boolean algebra provides identities like the distributive law. A multiplied with B plus C in bracket equals AB plus AC. Circuit equivalence means two different implementations produce the same outputs for all inputs. Using algebra to transform and simplify designs saves gates, power, and delay, key goals in real hardware. Properties of Boolean algebra. Here are some core Boolean properties you'll use constantly. Identity and null laws, idempotent and involution properties, complement, cumulative and associative laws, distributive laws, De Morgan's laws, and absorption. Mastering these lets you shrink a design without changing its behavior, often turning a complex-looking schematic into something elegant and efficient. Addition at the logic level happens in a binary, one bit at a time. Specialized circuits called adders implement this operation. By chaining single-bit adders, we can add multi-bit numbers. Understanding adder is foundational because the same patterns extend to subtraction, comparison, and arithmetic logic inside a CPU. A key wrinkle in binary addition is the carry. For single bits, 1 plus 1 equals 10 to producing a sum of 0 and carry of 1. A half adder computes exactly that. Given bits A and B, it outputs sum and carry. The truth table shows sum equals 1 when exactly one of A or B is 1, and carry equals 1 when both are 1. The half adder circuit captures those rules. Sum equals A XOR B implemented with XOR, carry equals AB implemented with AND. That pairing mirrors our earlier gate definitions. By wiring many half-adder-like stages and handling carry between bits, we approach full multi-bit addition. A full adder extends the half adder by accepting a carry in from a less significant bit. It outputs both a sum and a carry out. Internally, you can think of it as two half adders plus an OR for the carry paths, or as an equivalent optimized network. Full adders are the units we chain to build ripple carry adders. Multiplexers. A multiplexer or MUX routes one of many data inputs to a single output using a few select lines. Think of it as a digitally controlled switch. With n select bits, a MUX can choose among 2 raised to n inputs. Multiplexers are everywhere. Data buses, ALU operand selection, and conditional moves all rely on them. Here is an 8 to 1 MUX example. 3 select lines S2, S1, S0 encode a value from 0 to 7 that chooses which data input D0 to D7 appear at the output F. Change the select code and you instantly route a different input through. It's a compact way to steer signals without physically rewiring. Circuits can also remember. When outputs are fed back into inputs, we form a sequential logic that stores state. This memory allows systems to count, hold configuration bits, and synchronize operations across cycles. The simplest memory element we'll study is the SR latch. An SR latch stores a single bit using cross-coupled gates. The inputs S set and R reset control whether the latch stores a 1 or a 0. There are multiple implementations, often using NOR or NAND gates, but the idea is same. Feedback creates stable state that persists after inputs are released. Operationally, we avoid asserting S and R in the forbidden combination noted by the design. The outputs, commonly labeled as X and Y, are always complements. Whatever value X holds is the current state. X equals 1 means latch stores a 1. X equals 0 means it stores a 0. This is our first, simplest memory cell. Integrated circuits, chips embed many gates on a single slice of silicon. The silicon die is packaged so its signals reach the outside world through pins or pads, letting us mount the device on boards. Integration brings speed, reliability, and compactness compared to wiring discrete components. Historically, we classified ICs by how many gates or transistors they contain, from small-scale integration up through very large-scale integration. The trajectory has been explosive. Modern chips contain staggering transistor counts, reflecting decades of miniaturization and manufacturing advances. Here is an example SSI chip that contains several independent NAND gates into one package. Designers use these building block ICs to prototype or to implement simple logic functions, wiring the pins to form large behaviors. The same idea scales to complex systems on chip devices. The most important IC in any computer is the CPU. A CPU chip exposes many pins to communicate with memory, I/O, clocks, and power. Inside, enormous networks of gates implement instruction decoding, arithmetic, and logic, registers, and control. Everything needed to execute programs at high speeds. Before closing, consider the ethical dimension. Different professional organizations publish codes of ethics that guide hardware and software practice. Compare how hardware-focused and software-focused group frame safety, integrity, privacy, and professional responsibility. Spotting the overlap helps you act consistently across roles. So think of questions like how are codes of ethics like, which is more focused on software side, and how do those codes differ? A historical reflection. A foundational book set the stage for digital computers, even if its author received little recognition at first. The key contribution was formalizing logic as basis for computation, ideas that echo through every gate and circuit we have studied. Quick knowledge check. What do we call the study of materials at nanoscale, below 100 nanometers? What is the 10th strand in a computer science education? And who explored the challenge of expressing thought using symbols? Use these prompts to connect materials science, curriculum design, and the philosophy of symbolic representation. And one more, what did Maurice Wilkes realize in 1949 about programming and its practical difficulties? And when people say computer ethics, what topics do they mean? Professional codes, societal impacts, security, or all of the above? Questions like this tie technical work to history and responsibility. I hope you enjoyed the class. I'll see you in the next part of this week 3 really soon. Take care for now. Bye.